Okay, again, updates, turn in missing assignments. We'll have notebook check and test soon. And we will have the climate graphs due next week. Number one, polar climates have blank temperatures and blank precipitation. This is from our notes from 2 days ago, because we didn't have class yesterday because of the testing situation. Number one, also got an answer. Cool. I always love participation. This is on page 9. Yes, page 9, Diego, page 9. Let me get you in attendance as well, Diego. 1 second. I got you already. Okay. So page 9, guys. Again, make sure you got a picture of that. Make sure you got a picture. I'll give you 10 seconds. Give you a moment. Okay. So we all know polar climates are obviously going to be low in temperature, guys. But surprisingly, their precipitation is also low. So for both Angel, and you'll see that there now, it's going to be low and low. So very cold, obviously low temperatures. But even though there's all this snow, it actually doesn't snow a lot. It's like a frozen desert. It does snow, but when it does, it just stays there permanently. So it just looks like, oh, wow, it snows all the time. Well, no, it snows, but when it does, it just never leaves. It stays there forever. Okay, so low and low. Next, we have what climates are going to experience the seasonal changes. Going to be experiencing falls and springs. Angel, did you maybe have a guess for that one? Mild, and what's the other one that has the extreme weather? Answers are on page 12 and 13, by the way. Continental, yeah. So for number 2, the 2 of them are going to be continental and mild. Again, all the other ones are either cold year-round or hot year-round. These 2 can have some variation with falls and springs and winter and summer, things like that. Next one, what climate type is the closest to the equator? Any ideas, Angel, what you think that is?
Dry.
Going to be dry. Perfect. Great job. So, yeah, tropical's close, but dry climates are slightly closer. And to finalize today's stuff, because it is kind of new, there's a term called rain shadow. Rain shadow is land that becomes dry like a desert because the mountains around it or near it drain all the rain clouds of their water. So as you see in this top right picture, when clouds go over mountains, it squeezes and drains and dumps all the rain on one side of that mountain. So all the area on the other side of the mountain becomes a desert. We call that rain shadow, okay? You go to deserts, a lot of times you're going to see mountains around the deserts. This is the big cause of that. I'm going to give you guys a moment to get that down. Wait for my in-person students when they're ready. And then, Angel, did you want to jog right to my chance? Or no? Okay. And as soon as my in-person students are ready, we'll move on because they're now on track. Yeah, questions or concerns that, let me know. Again, you're going to need this stuff for the notebook check coming up soon. I'm good? Okay. Let's go ahead and move on then to our, I'm going to skip the table of contents today because I don't think it's anything new. Let's do our first practice question of today. This is something I think we did maybe, we know about this a little bit. We think we've gone over this a few days ago. Okay. One moment, guys. One moment. Again, be ready to answer this question in the chat. It's another fill-in-the-blank question. All right. Here we go. Vegetation, also known as plants. Typically, blank precipitation and blank temperature within an area. Is it going to increase both? B, decrease both? C, increase, decrease? Or D, decrease, increase? So how do plants affect the rain? And how do plants affect temperature? Give it your best guess. Again, for participation points, guys, you need to answer this in the chat. The participation gets added up the end of the quarter. And that can round your grade up. Let's see. When you're ever ready, Angel, I can see your card. All right, great job. See what you got. I need more people to answer in the chat, guys. Let's see. Thank you, Sanaya. Thank you, Sanaya, for your answer. Again, what do, Daniela, thank you. Again, what does vegetation do? Thank you, Diego. I'll give shout outs here in a little bit. What does vegetation? Michaela, great. Thank you, Michaela. Lakia, thank you. Yorkies, great. Thank you for participating, guys. Again, you're going to see a lot of these questions get reused on the online test. So good to participate. I got 10 seconds, guys. I think I still need Joseph. Answer, Melissa, answer, right? Okay, let's check out our answer, guys. Our in-person students said that we had letter C, increase, decrease, and that is correct. Plants are going to make it rain more because there's water flowing through the plant's body. And they're also going to make temperatures cooler because they absorb sunlight. Just like on a hot summer day, the grass always feels nicer than the sidewalk. I want to give shout outs to Angel, Lakia, Michaela, Diego, Daniela. Awesome job getting that right. Again, everyone else, you still get participation as well for participating. So good job, everybody. Good job, everybody. Okay, let's move on, guys, to our first video question of the day. Keeping things at a good, fast pace, right? All I want you to do on page 9 or 10, preferably 9, is just write this question in red. We all know about climate change, right? Angel, are they saying it's getting hotter or cooler? Hotter. They're saying it's getting hotter. We all know that, right? It's been told to us time and time again. But I want us to know for today, what evidence do they have of that? What proof do these scientists have that the climate is changing, right? What proof do they have that can convince me to that being the true situation? Because in a lot of things, guys, we got to find find proof, find evidence, right? With a lot of things in science. Okay. So why are scientists panicking? Why are they making such a deal out of climate change? What evidence, what proof do they have? You're just gonna write in bullets a few of the ideas listed in the mentioned in the video. So let's go ahead and take a look. Angel, did you have any thoughts or ideas as to far evidence that they could have beforehand? No? Okay. Let's check out again and just jot down 4 to 5 bullet down ideas from our first video today. I'm just going to play 3 minutes of this, guys.
The work that we do now
one moment.
Handy reference.
So science, evidence behind climate change.
The sun is the source of warmth on Earth, so thanks for that, sun. Ice and clouds reflect some of its light away, but the rest is absorbed by land and water and re-emitted as heat. Some of that heat escapes to space, and some is held in by the atmospheric greenhouse effect. The insulating effect of Earth's greenhouse gases are the reason that life exists as we know it, but human activities have increased the concentration of one of them, carbon dioxide, 40% since the Industrial Revolution. We know the sun's output has varied during history, but since the 1970s, the period when global temperatures increased the fastest, temperature and solar activity have moved in opposite directions. If the sun was to blame, it would cook the upper and lower layers of the atmosphere together. Instead, we only see warming in the lower layers, the same place that human greenhouse gases like carbon dioxide are piling up. Since 1870, with fossil fuels, cement production, and land use combined, humans have put about 2,000 gigatons of CO2 into the atmosphere. That's 2 million tons, and about 40% has stayed there. Studying gases trapped in ice cores has let us see what Earth's atmosphere was like in the past. At more than 400 parts per million, today's carbon dioxide levels are the highest they've been for almost a million years. That's before humans even existed. Totally uncharted territory for us. More carbon dioxide in the atmosphere means average temperatures across the globe are increasing, and fast. Right now, Earth is warming about 10 times faster than at the end of an ice age. Okay, so CO2 is increasing. How do we know it's our fault? The best evidence comes from looking at what isotopes, or different kinds of carbon, are in the atmosphere. Fossil fuels come mainly from old plants. Plants prefer to use the lighter isotope carbon-12 over the heavier carbon-13, so they contain a higher ratio of 12 to 13 than the atmosphere does. When more fossil fuels get burned, the percentage of carbon-12 in the atmosphere should go up, and that's exactly what we see. And it's not because of volcanic activity. Volcanoes only emit about 1% as much CO2 as we do. Normally that CO2 is balanced and exchanged between the atmosphere, plants, and animals, but eliminating carbon sinks has released centuries worth in just a few years. Other greenhouse gases are also increasing, like methane from farm animals and natural gas processing, or nitrous oxide from fertilizers. If we run simulations just using natural causes of climate change, they predict no change or even cooling in the 20th century, and that is not what's happening. It's still going to get cold in some places, but in the 2000s there were twice as many record highs as record lows. And each of the past 3 decades has been warmer than any other decade since we started measuring in 1850. Since 1900, actual temperatures around the world have increased almost a full degree, and most of that has happened since the 1970s. Looking at data from tree rings and ice cores, the past 30 years is probably the warmest in 8 centuries. Of course, not every place on Earth warms equally. Oceans cover more than 70% of Earth, and they absorb more than 90% of the heat added to the planet. Naturally, that's where we see the most extreme changes. Around the world, oceans are rising 1/10 of an inch per year, and they're up 8 inches since 1901. This
All
is
right,
because
so a lot of different lines of evidence. Angela, did you want to list off a few that you wrote down?
The temperature number, the greenhouse gases,
Okay,
the Earth heating more than it should, and the ocean rising more.
absolutely. So temperature numbers, greenhouse gases, ice caps melting, sea levels rising. All those are good answers. There's going to be 4 that I want you guys to focus on today. So let me go ahead and show Angel what we need on the screen to set up on page 10. And I'm going to show you guys as well what we need to set up for page 10. So go to page 10. You're going to title it Climate Change Evidence. Climate Change Evidence. And the 4 I want you to focus on are right here. Okay. Here's the top 2, and then here are the bottom 2. Okay. I'm going to leave this here, freeze frame. You can take a picture of that. So go ahead and leave this up for a little bit. Take a picture of that. Top half is at the top half. Okay. Our first example is going to be ice core samples. Second example is seafloor sediment. Okay. Anybody else need that? All right. And then here's the bottom half. Here's the bottom half, guys. I've got fossil record. It's a little T-Rex skull. Got a little seafloor there, and I got little ice cubes on the ice core samples. And then last one's a little tree stump. Tree rings, tree rings. Okay. Leave that for 10 more seconds. Okay. When our in-person students are ready, I'm going to go ahead and start off the first one. Okay, so be patient. Try to draw that, write that out on page 10 while you're waiting. Have those pictures there, keeping things at a good fast pace. And what I typically did with this activity was I would go over the first one. If you guys were here, I'd let you guys research with your phone the other 3 with like some questions. So like, how is seafloor sediment evidence for climate change? How are fossils and tree rings? But for conveniency, given the e-learning, I'm going to go ahead and just go through them one by one with you guys. That'll save us a lot of time and effort and confusion. Okay, so if you're waiting, get that set up. As soon as our in-person students have their setup ready, we'll get started. So it may be about 2 or 3 minutes. So take a 2-3 minute break to get your stuff set up. Again, we have 4 categories. Climate change evidence. We're going to start back up here in about 2 minutes as soon as our in-person students have their setup finished. So again, guys, take a moment. We're setting up page 10. Climate change evidence, 4 sections. Ice core samples, seafloor sediment, fossil record, and tree rings. As soon as the in-person students are ready, we will begin here in about 1 to 2 minutes. All right, so let's go. Let's begin with ice core samples. Okay, again, it looks like somebody signed out, so keep in mind, don't sign out, guys. Oh, okay. So let's go ahead. Let me share our screen here again. Okay, so ice core samples. Well, when you look inside of ice, what sometimes gets trapped inside of ice, Angel? Not fish, but think of what else? Not bones. What are little specks and little white specks in ice sometimes? The clear specks.
Air.
Yep, air bubbles, right? Perfect. So for number one, the first one, guys, ice core samples, we're just going to say this. Just write what's in red there. These ice samples sometimes and a lot of times trap air from thousands of years ago. Okay, because if we dig deep, the ice has been preserved for thousands of years, and if they drill deep enough, I'll make sure the mic's off, guys. Okay, thank you. Okay, so sometimes again the ice guys, if they drill deep enough, they can have ice from the Ice Age. They can get ice from just 100 years ago, right? So pretty recent. And what they've done is they can look at the air bubbles trapped in that ice and compare how was the air before there were any factories and cars, just like 200 years ago, like 1800s. They can find that and look at it and see the difference. That's how they're able to know that, there's a lot more carbon dioxide in the atmosphere now than there was just a couple hundred years ago, right? They look at all the bubbles trapped in the ice, and they drill it out from Antarctica and some from the North Pole. Okay, so it shows how the atmosphere has changed over time when they melt that ice and examine the gas bubbles in the sample. So let's take a look at, since our in-person students are ready, I'm going to show you guys a quick video clip that gives us a glimpse of how those samples are collected and studied by scientists. Again, people don't live on Antarctica, but there are scientists who live there for a few months at a time to conduct experiments.
It's a busy, freezing cold day inside the National Ice Core Lab in Denver, Colorado.
We're going to cut gas samples out of this core.
Scientists from Maine to California here to cut pieces of precious Antarctic glacier ice to take back to their labs for study.
We started the Ice Core project in 2005.
With support from the National Science Foundation for a project called the West Antarctic Ice Sheet, or WAIS Divide, lab manager Mark Twickler and a team of scientists, engineers, and support personnel traveled to the bottom of the world to drill out and bring back these ice cores. The goal of the project? To collect and study perfectly preserved records of the distant past.
The unique things about polar glaciers is each year that it snows there, the snow never melts. So you get 1 year of snow on top of the next year of snow. It compresses, so everything that fell out of the atmosphere, dust, salt from the ocean, volcanic ash, is preserved in that ice core.
This particular ice sheet is more than 70,000 years old. The team drilled down more than 2 miles into it to retrieve these cores, which were then flown to the U.S. and stored in a giant 40 below zero freezer here at the Ice Core Lab.
Inside this freezer contains more than 10 miles of ice cores collected from around the world.
Twickler says the ice core's layers are like tree rings, each layer representing a year of weather and snow.
We can tell what
See the bubbles in a second?
temperatures were. We can tell how rough the oceans were around Antarctica. We can tell how dusty Australia was.
Scientists are keen to study the bubbles trapped in the cores, each a tiny pocket of air frozen in time.
We can measure a variety of gases that were in the atmosphere at the time the bubbles were formed.
Other scientists want to know
So a
how
really cool glimpse of that as well. Let's move on now to seafloor sediment. Seafloor sediment, guys, just two quick bullets. Okay. The seafloor sediment, seeing how it moves over time, can show us the sea level change. Thanks to this, we now know that the sea levels were a lot lower during the Ice Age because a lot of it was frozen. And again, sea levels do change naturally, but there's concerns because they're seeing sea levels change more rapidly at a higher rate in a short amount of time. I think the sea levels have changed like eight inches maybe in just the past 100 years. So they're almost a foot of a difference for those sea levels nowadays. Okay. And also we can see the soil composition. How was the rock and the land different during the Ice Age and when the dinosaurs were around, et cetera, et cetera. Really cool there. Okay, everyone make sure you got a picture of that. We're going to move on now to our third one. I'm going to skip the video for this one because I don't think we need it. It's more about coral reefs and stuff. Fossil record, fossils, guys. Well, think of it this way. If I find a fish fossil in a desert, what does that say about that area in the past? That fish were there, which means there was what in that desert? Water, right? So that's the idea. How does an animal fossil tell me about climate? Well, in the Grand Canyon, there's a river at the bottom, but in the very upper parts of the Grand Canyon, they found fish fossils. And they now have evidence that the Grand Canyon might have been a massive lake or a massive part of the ocean in the past. That may have been what dug up that huge, massive opening in the ground. Okay, so we use what's called carbon dating. We look at how much carbon is inside the fossil and how fast it's degraded to really see how old that fossil is. So whether it's 10,000 years old or 100,000 years old, right? So that's the idea. Use carbon dating and what fossil it is. Again, there's no longer any bone in that fossil. It's all mineral, but it's like mineral that morphed with the bone. So the bone's gone, it's all mineral, but it just kind of took shape with the bone. We've got one more video question and one more section, and we will call it a day, everybody. One more video, and the video is about El Nino and La Nina, which for many is confusing. So I'll kind of try to break that down a little bit to make it more relatable and understandable. So let's go to that. You guys are going to move on back to page 9 or 10 or 14. Any one of those pages, page 9 or 10 or 14. You okay, Angel? You need a little break? Okay, good. All right. So again, no need to rush, Angel. Here are 2 video questions. I want to know for El Nino, La Nina, which one is warm and which one is cold, right? This has to do with how the ocean affects climate, because the ocean has a huge impact on our everyday weather and our climate. So as soon as our in-person students are ready, I'll play this video. Again, which one's cold, which one's warm, and then how does each affect the southern United States, right? All right, so I'll give you guys a moment for that. When our in-person students are ready, we will begin. So El Nino, La Nina has to do with the ocean, No rush, no rush. 2 more videos and one more thing after this. Let's check it out. El Nino versus La Nina. What's the difference? Who's cold? Who's warm? How do they affect the southern U.S.? Let's go and check it out.
In Spanish, it means the Niño, El Niño. We all know that in Spanish, it means the Niño. El Niño! But what is El Niño? What about La Nina? What do they mean? I'm meteorologist Jason Myers, and El Niño and La Nina are both complex weather patterns that alter the entire weather landscape around the world. El Niño and La Nina are opposite phases of what's called the El Niño Southern Oscillation, or ENSO cycle. Both take place in the east central equatorial Pacific Ocean. In other words, off the coast of South America. During an El Nino year, there's an upwelling of warmer water off the coast of South America, and in a La Nina year, there's an upwelling of colder water. This difference in ocean temperatures then alter the weather around the world. Since oceans cover roughly 75% of the planet, they play a big part in our weather patterns. So when we see a big temperature swing over a large section of the ocean, it changes weather patterns worldwide. For the United States, an El Nino event will typically bring a warmer, drier winter to the northern half of the United States, while the southern half of the U.S. gets a colder, wetter winter. A La Nina will typically bring dry, warm winter weather to the southern U.S. and slightly wetter and cooler conditions to parts of the northern U.S. between the months of December and January.
So just to save us time there, guys, El Nino and La Nina are basically the what of each other? The opposite, right? So for number one, who's warm and cold, Angel?
El Nino is warm and La Nina is cold.
So El Nino is warm and La Nina is cold, right? So El Nino warm water, La Nina cold. So I always say this. Think of it like if two people have a crush, right? The boy is going to approach the girl usually, right? So the boy wants to warm up to the girl, but the girl gives the boy the what shoulder? Gives him the cold shoulder, right? That's what I always say. So he's going to try to warm up to her, try to say hi and get to know her. The boy is, and then the girl, she's going to act distant and cold. So that helps me remember it, right? But then she acts cold, so he gets basically rejected, right? So things go south. We're talking the southern United States here in Florida, right? So for him, things went south. So how's he going to try to act after he gets kind of rejected? Tries to play it what? Play it cool. So then in the south, he's going to act cool, but he's kind of anxious, so he's sweating, so he's wet, right? Kind of act cool. He's going to act cool about it. He's not going to get upset, get mad. He's just going to keep his cool, right? And after a while, La Nina does begin to warm up to him as a friend, right? So when he tries to, take her on a, date or this and that, she still kind of keeps him at a distance and the friend just as a friend, right? So it's a silly analogy. It can be confusing, but the analogy helps me remember it. So again, boy and girl, boy wants to talk to girl gives him the cold shoulder. He gets rejected. He tries to play it cool, a little sweaty, so he's anxious. And then she eventually warms up to him, just the opposite, warm and dry. So cool and wet in the south for El Nino, cool and warm and dry in the south for La Nina. Let's go again. Make sure you got a picture of that, guys. Got a picture. Give you a moment. Don't mean to babble on too much. Let's do our last section of the day. Okay. Tree rings. Tree rings tell us the what of a tree, Angel. What was that? The years, the age of the tree. Last section, guys, on the bottom of our page 10. If you didn't know, guys, trees can live up, I looked this up, trees can live up to 5,000 years. I mean, most trees are like 100 to 200, couple hundred years, but some trees can live up to thousands of years. Amazing, incredible. So if you have an open tree or you collect a sample of a tree, inside of it, there's a ton of rings, okay? These rings represent how the tree has grown over time. If the rings are really far apart, that means it rained a lot that year. The tree grew a lot that year. If the rings are really close, that means the tree did not grow much at all that year, which means there might have been a drought. Okay, so that tells us within the time span of that tree living, it tells us what kind of weather we had those certain years. Okay, if there is a darker scar mark on the tree rings, that means there might have been a forest fire that year. Okay. So it tells us the age of the tree and shows us when there were droughts and when there was a lot of rain. Okay. When you guys are ready, I'm going to have, actually, most of our classes didn't get this far. Let me though, we'll play one more video and then I'll take attendance and we'll call it a day. So one more video, take attendance, and we will call it a day. So last thing. Okay. So let's check out our last video, guys, our visual, before I take attendance and, we get going here for tree rings.
When you look over a forest in Utah, whether from an airplane or hiking around, you might not realize that there's a library of information in those trees. Each tree is recording information about the environment that it's growing in.
The main focus of my work right now is to try to reconstruct stream flow from tree rings. The process is dendrochronology, so dendro for tree and chronology for time. We primarily take very small core samples. They're about the diameter of a pencil with a hand drill, and then we take it back to the lab. By cross-dating the rings in this dead tree with living trees, we'll be able to identify when this tree died.
Then we follow that up by measuring the rings to 1,000th of a millimeter, so it's very detailed work. When we have droughts, the rings are very narrow, and the more extreme, the narrower the ring. As we're trying to identify patterns in wide and narrow rings, you can kind of think of that as a barcode in the food that you might buy in the store. Trees in an area are going to have not exactly the same pattern, but a similar pattern of wide and narrow rings, just like that barcode. We get to the point where we could just look across a sample and say, okay, there's 1580 and there's 1735. We know where those difficult years are.
We're able to look at the records in the rings and from that reconstruct stream flow much further back than we can just with historical records. In some areas, under the best conditions with the best species, we can have up to a 10,000-year record from tree rings. We have
So
maybe
again,
52.
this is just in the West Coast. They've got trees that are 10,000 years old. So really cool there. Good sample of that there. Okay, let's go ahead and take attendance. Just as a reminder, guys, again, no assignments due this week. You've just got to have the climate graph done before next week, and then any late work, you got to get it done right away, right away. Let me do a head count here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So we might have somebody who joined us. So let's see, Daniela, I've got. Michaela, I've got. Sanaya. I've got Diego. I think I've got Lakia. Okay, Yorkies and Joseph and Melissa. And let me get Angel here. Yep. Okay, guys, you were all good to sign out. You may now sign out. I'll see you guys tomorrow. If you have questions, let me know. Good job, everybody. Yeah, I'm going to sign out in 10 seconds unless anyone has questions.